All right, next we're going to look at reduction of esters to alcohols. This can be accomplished using a lithium aluminum hydride. Okay, this is very similar to nucleophilic acyl substitution. Hydride is the nucleophile. Alkoxide is then kicked out. The resulting aldehyde, though, is further reduced by lithium aluminum hydride. So here, hydrogen or hydride is replacing the OR group. A second hydride then attacks. This is a nucleophilic addition reaction. This forms a lithium salt, and when you add dilute acid, you'll get a primary alcohol. Right, so when we reduce an ester, the alcohol will always be primary. You'll have another alcohol, of course, produced, whatever was present here with the alkoxide. Okay, if we want to stop at the aldehyde, okay, we actually looked at this in an earlier chapter, the chapter on aldehydes and ketones. We can use a reagent such as lithium tritert butoxyaluminum hydride. This has three bulky tert butoxy groups. It only has one hydride equivalent. And then this is often done in a dry ice bath, minus 78 degrees. So that slows down the reaction considerably. This will react faster with the acyl chloride than it will with the aldehyde that's produced. And so you can stop at the aldehyde stage. Lithium aluminum hydride will reduce primary, secondary, and tertiary amides to the corresponding amines. Okay, notice that unlike with the esters, there's no alcohol group present. There's no oxygen. The oxygen ends up binding to the aluminum. Okay, so here's a specific example. We have acetanilide or N-phenylethanamide. Okay, when we reduce that, we'll get N-ethyl aniline. Nitriles can be reduced to primary amines. And again, this is a review of what we saw in the amines chapter. We can either use catalytic hydrogenation. We add hydrogen to both sides of this triple bond, 2 hydrogens to each side, or we can use lithium aluminum hydride, okay, followed by the addition of water. Acyl chlorides and esters can react with Grignard reagents and organolithium reagents to form tertiary alcohols unless we have a formate ester, in which case we get a secondary alcohol. But the Grignard or lithium reagent reacts twice. Okay, upon hydrolysis, we get our alcohol. Okay, here's the mechanism. This is starts out just like it would with an aldehyde or ketone. The Grignard attacks the carbonyl. Instead of the oxygen getting protonated, though, oxygen pushes down, kicks out the alkoxide. The resulting ketone then reacts with a second equivalent of Grignard reagent. Nitriles can react with one equivalent of Grignard, and this gives us a ketone. Okay, the reason the ketone doesn't react is it's produced on hydrolysis after the Grignard addition is finished. Acid chlorides can be synthesized from carboxylic acids, most commonly using something like thionyl chloride or oxalyl chloride. Okay, this works very well. It's very convenient because the byproducts are all gaseous, so they can be easily removed. That prevents the reaction from going backwards. Okay, so here's a summary of acid chloride reactions. Okay, with water, we get a carboxylic acid. With an alcohol, we get an ester. With an amine, we get an amide. With a carboxylic acid, we get an anhydride. Okay, notice that in all of these, the byproduct then is HCl. Acid chlorides can also react with Grignard reagents, two equivalents, to form a tertiary alcohol. We can make ketones using a Gilman reagent. Okay, notice only one of these R primes actually reacts. We can reduce an acid chloride to a primary alcohol using lithium aluminum hydride. We can reduce it to an aldehyde using lithium triterpenoxy aluminum hydride. Acid chlorides are also useful reagents for the Friedel-Crafts acylation. Okay, as long as we don't have anything more deactivating than a halogen on our aromatic ring, we can produce a phenylketone or acylbenzene. Okay, in this example, anisole is an activated ring. The methoxy group is activating. We get mostly the para product. Anhydrides can be produced from acyl chlorides using carboxylic acids or carboxylates. Okay, we can also produce mixed anhydrides if we want, such as acetic formic anhydride. Pyridine is sometimes used to deprotonate the acid and form the carboxylate. Anhydrides undergo hydrolysis to form carboxylic acids. They can react with alcohols to form esters, with amines to form amides. And notice that the byproduct in all of these is a carboxylic acid. This is something we haven't looked at before, but you can do a Friedel-Crafts reaction using an anhydride. Okay, this requires a Lewis acid catalyst, something like aluminum chloride. Okay, here's an example of using a cyclic anhydride. Okay, the anhydride is more reactive than the carboxylic acid, so we can stop it at this stage. Acetic formic anhydride. This is a good reagent for making formate esters and formamides. The formic acid part of it is more reactive than the acetic acid part. Esters can be hydrolyzed to carboxylic acids and alcohols. We can do transesterification. We can do ammonolysis. We can reduce esters to primary alcohols. We can also react esters with two equivalents of Grignard to form tertiary alcohols. Lactones or cyclic esters are most easily formed if we are making a 5 or 6 membered ring. For larger rings, one of the ways to make these lactones is to remove the water as soon as it's formed. But these are made from carboxylic acids. Okay, so we have elimination of water and cyclization to form the ester. Amides can undergo hydrolysis to carboxylic acids or carboxylates, depending on whether we're doing it in acidic or basic solution. They can be reduced with lithium aluminum hydride to amines. Okay, this is a reaction we looked at back in the amines chapter. That's the Hoffman rearrangement, where the difference here between this one and the one above it is that we have one less carbon than what we started with. Okay, that's eliminated as carbonate. And then this is a new reaction that we'll look at momentarily. Using a dehydrating agent such as phosphorus oxychloride or diphosphorus pentoxide, we can make a nitrile from a primary amide. Okay, this is dehydration because if you look at the difference before and after, we've eliminated water. Phosphorus oxychloride would produce phosphoric acid and 3 equivalents of hydrochloric acid. Diphosphorus pentoxide would form 2 molecules of phosphoric acid. Okay, these are both really strong dehydrating agents. We can form lactams from amino carboxylic acids. And again, the most favorable, the easiest ones to form are the 5 and 6 membered rings. Okay, I mentioned earlier beta lactams. This is an important group or moiety in penicillin and cephalosporin type antibiotics. The 4-membered ring is unusually reactive, largely because of ring strain, and it can react with a variety of different nucleophiles. Okay, so the nucleophile attacks the carbonyl, and in this substitution reaction, the ring undergoes opening. Nitrogen then picks up a proton from water. And the way that these work is that an active enzyme uses a alcohol group, or it could also be an amine group, to attack the carbonyl, and this gives us an acylated, deactivated enzyme. And the way that these kill the bacteria is by interfering with the synthesis of bacterial cell walls. Nitriles are included in this chapter because they can be hydrolyzed to carboxylic acids. The intermediate in this hydrolysis is a primary amide, which, of course, we saw earlier could also undergo hydrolysis. Okay, this is a reaction we've seen before. Nitrile can react with 1 equivalent of Grignard to form a ketone. Okay, next we'll look at thioesters. Okay, notice here we've replaced the ether oxygen with a sulfur, and in this resonance structure we have strong pi overlap, but then we have poor pi overlap with the CS double bond. Okay, because these are unequal in energy. Okay, so what's the significance of that? Both in the fact that we can transfer acyl groups, such as an acetyl group, and the fact that thioesters are not as easily hydrolyzed as carboxylate esters. Okay, so here is a biologically important thioester. Okay, this is coenzyme A, or acetyl coenzyme A. A nucleophile taxocarbonyl. The coenzyme A thioate is a good leaving group, a very stable leaving group. And so this reaction serves to transfer an acetyl group to a different molecule. Okay, and this is very, very important biochemically to be able to transfer acyl groups. Okay, next we'll look at carbamate esters. Carbamate is a compound in which we have an ester on one side and an amide on the other side. When isocyanates react with water, we get a carbamic acid, which is not stable. The carbamic acid quickly loses carbon dioxide and gives you an amine. This was actually one of the steps in the Hoffman rearrangement. Okay, when an isocyanate reacts with an alcohol, we get a carbamate ester, or a urethane. Okay, this particular compound, 7-insecticide, is made from methyl isocyanate and 1-naphthol. This reaction is particularly infamous back in 1984 in Bhopal, India. A large quantity of methyl isocyanate was released, and many people were killed because this is very poisonous. Okay, here we have phosgene. This can be thought of as a double acid chloride. This is a gas, and it can react with a dialcohol such as bisphenol A. Okay, so we form an ester on both sides, and then we form another ester and another ester, and this keeps repeating itself, and we end up with a polymer. This particular polymer is called lexan, and lexan is a very tough and transparent material. It's used in, for example, shatterproof eyeglass lenses. Bisphenol A, or BPA, has been in the news lately. It's evidence shows that it's an endocrine disruptor. You may see labels on plastic water bottles or other plastic items that'll say BPA free. Okay, here we have a diisocyanate and ethylene glycol, which is a diol. And when these react, we get a polyurethane. Polyurethanes are used for insulation. They are also used for materials such as the wheels on rollerblade skates are made of polyurethane. Okay, it's a very tough material. And that concludes our lesson on carboxylic acid